702.
The Naked Scientist.
Chris Smith joining us live on the line from the UK. I hope you've had a good week in spite of Brexit, Chris.
Good morning, Nicholas. To be honest, I reckon alongside most of the population of the UK, I've developed profound Brexit fatigue. I just turn it off now. I've no idea what's going on. I don't think the politicians know what's going on. So actually, I just don't watch it anymore.
I can't blame you. We'll kick off with the Scottish have found a way to make plants use 50% less water, but without reducing their productivity. It's an amazing boon there and could have enormous implications for food production in places that don't have much water.
Yes, agriculture accounts for some 50 to 70% of the fresh water consumption of the entire world. And it's pretty important, obviously, because we have a growing population and people need to eat. And therefore, if we can halve the water consumption of producing food, at least the plant-based aspects of that food, then we can make a major dent in the sustainability problem that we face in the future. This is a story, it's in the journal Science this week. Mike Blatt, who's a professor of botany at the University of Glasgow, has bioengineered some plants so that they are much more efficient at water consumption. Now, the way he's done this is he's added a gene to a cluster of cells in the plant called guard cells. Guard cells open and close these pores on the undersides of leaves called stomata. And these are essential to the plant because when the plant opens these pores, it lets in carbon dioxide from the air, which is how the plant grows, because it uses the carbon in carbon dioxide and it turns it into sugar. And the sugar, it then builds up into all the tissues in the plant. And the oxygen that's left over, it spits out and we breathe that. The problem is that in order to get the carbon dioxide into the leaf, you have to open these pores, and because the inside of the leaf is wet, because that helps the carbon dioxide to dissolve and then get distributed inside the plant tissues, the plant ends up losing water. It's rather like us. When we breathe out the water from the wet surfaces inside our lungs as well. So what he's done is to make these guard cells much more sensitive to light and much more rapidly reactive to light. So when a cloud goes over, at the moment the plant can't really react to the fact that the light intensity has changed because its responses are too slow. But with the modification that the team from Glasgow have made, the plants can now react far more rapidly, and that means they can close these pores when there's not enough light to make the plant photosynthesize effectively, and then reopen them again very promptly. And the result of that in tests in their laboratory, these are lab tests, they're not field tests, that shows that the plants grow just as much, but they use up to 50% less water. And they're now doing studies to try to move the same genetic elements that they've used to do this, the same tools, into important agricultural crops like rice, soy, and cereals. And I asked Mike, well, when's this going to happen? And he said, watch this space because this is happening right now. We're doing the tests.
In terms of take-up elsewhere in the world, I mean, if it's only going to leave the lab, in best case scenario, a couple of months from Scotland, how long do you think it would take for something like this to take root around the globe and reach the parts of the world that it's really, really needed?
Well, the thing is that whenever you make any kind of big dramatic change like this, you have to do very careful experiments to make sure that you're doing no harm. Because as I put it to Mike Blatt, then when you grow a plant like this in the soil, if it's extracting all the same amounts of nutrients, but it's changing the amount of water that's flowing through the soil, this could have profound effects for the microbiome in the soil. It could have profound effects for the distribution of water in soil. It could have profound effects for the way in which minerals move from deeper layers up to the superficial parts of the soil. Those tests need to be done before we were to deploy this on a mass scale around the world to make sure that this is safe. And also to make sure that we understand what we've done to the plants, because although they are pretty sure that the genetic changes that they've made work the way they think they have, whenever you make a genetic change to an organism, one has to be really excruciatingly careful that there haven't been some knock-on, so-called off-target effects that could have subtle changes to the way that organisms behave, which could, although they're not directly affecting the way the thing grows or the way it looks to us, they could have subtle biochemical effects, and those could have consequences of all kinds. So it's very important before we just say, right, we've solved this problem, let's all use it, we have to do very careful experiments, and that's what they'll be doing to make sure this is safe and effective and sustainable.
It's the Naked Scientist, Chris Smith, joining us on the line from the UK. Abby and Oakdean, good morning.
Good morning, Chris. What would happen if you stopped to think and forgot to start again? What would happen?
serious question. Dreams. I read that you dream often during the night, about 10 times. But I also read that dreams actually only last a very short period. And I have such incredible, intricate dreams. I'm just wondering, does anybody know how long they actually last, dreams?
Abby, well, the answer is that we have reasonable insights into when we dream, how often we dream, and how long dreams last for, because we can measure the brain activity that goes along with them. When you go to sleep, sleep is not a binary thing, on or off. Sleep is a complex series of brain changes and brain electrical changes, and those evolve as the night goes on. So when you first go to sleep, your brain activity is quite different from the times at which you're dreaming and the time at which you wake up. Now, what we do understand about dreaming is that when you first drop off and you start to dream, then you change your brain activity in quite a profound way, because people do these experiments. You take someone to a sleep lab, you put electrodes on their head which measure the currents from the underlying brain activity through the scalp, and this tells you what bits of the brain are doing what. And when people go into a phase we call rapid eye movement, REM sleep, and it's called that for the very reason that people's eyes are moving around a lot behind their eyelids. If you wake them up when this is happening and ask them, were you dreaming about anything? More often than not, they'll say they were. So when people are in the REM phase of sleep, this is when dreaming seems to happen. This happens periodically through the night, and as you go through the night, the periods of REM sleep get longer. And the accounts given by people of the richness of their dreams increases with the duration of that REM sleep. And so you tend to have your richest dreams and your longest dreams later in your sleep cycle. So in other words, just before you wake up. And therefore, the reason we probably remember our dreams and we remember the richest dreams is because those are the ones that happen just before we wake up. And because most dreams are just brain activity that we then dispatch with, you then remember the ones that happened most recently because you wake up when they were happening or just recently after they finished. And that's probably why we get these very rich dreams later on. But it's certainly not an all or nothing thing. And we don't know why we dream. We don't know why we sleep, actually. But we do know that both are critical for both physical and psychological well-being.
Very, very good answer. But then bottom line is, we don't actually know how long they last.
Well, those cycles last a number of seconds when you first go to sleep to minutes when you end your sleep phase. But the thing is that when you are dreaming, what is happening is that these different brain areas that do different jobs when you're awake, so the parts of the brain that do seeing and the parts of the brain that do language, they become spontaneously and independently active, and they generate a response or a series of activity patterns which you interpret. They're presented to your unconscious as that particular experience. Now, the way your brain keeps track of time normally when you're awake is that it's got this sort of log of all of these memories, and it knows roughly how long they occurred over, and so it sort of divides how many memories it's got by the time it must have occurred over and works out what the timeline is and how rapidly it all happens. When you go to sleep, all of these memory impressions are basically generated almost instantly. So your brain doesn't really have any idea how long it all took. So it gives the impression that there was this long, detailed, sort of evolving story. But in fact, it was probably generated in a flash.
Abby and Oakdean, thanks very much for that. And of course, the page with the questions has just gone blank. I'm going to paraphrase an SMS. I apologize, David, if I don't get this right straight off the bat, but he wants to know how exactly did Einstein, quote unquote, his hero, go about to accurately measure the speed of light?
Well, Einstein didn't accurately measure the speed of light. Einstein was lucky enough that many other people already knew a lot of this stuff. Einstein knew that there was a finite speed of light, and his intellectual leap was that there was this speed limit. It was the speed of light. It was going to be the same everywhere in the universe, regardless of who measured it. And for that reason, because the speed of light is invariant, can't change, time and space-time has to warp to accommodate the fact that light always travels at the same speed. So putting this another way, if I drove past you and I was firing a pea shooter at you on my way past, the pea would hit you at the speed of the pea leaving the pea shooter plus the speed of the car. But if you did the same experiment with light, what you would measure is light travelling at the same speed regardless of how fast the car was going, whether you're in the car or whether you're at the side of the road. And because light always travels at the same speed for both the observed and the observer, then the time that we measure has to change to keep things balanced, and that was Einstein's leap. The first measurements of the speed of light were made many hundreds of years ago, before Einstein. One of the most amazing pieces of observation, a guy called Ole Rømer, who is an astronomer, actually looked at the moons of Jupiter, and he was looking at Io specifically, and he knew that these moons were going round Jupiter because he could see them, but he also noticed that at certain times of the year when he made this measurement of Io orbiting Jupiter, it would arrive a bit late. And at other times of the year, again, it would arrive apparently a bit early. Now, they knew how big the circuit it was doing was, and they knew it was going around in a big circle. They therefore knew how long it should take. So how could you possibly get something arriving maybe 8 to 12 minutes early at certain times of the year and 10 minutes late another time of the year? And then he realised that time difference is because the Earth and Jupiter are on different orbits, and at certain times of the year the Earth is as far from Jupiter as it possibly can be, and the time difference between the light travelling from Io to the Earth corresponds to the distance across the solar system between the Earth and Jupiter. And that therefore means that's how fast light must be travelling. And because they knew how far it was between Earth and Jupiter, they could work out the speed of light. So these people hundreds of years ago actually got a very impressively accurate measurement for the speed of light just based on observation. Incredible.
Indeed. Thanks very much for that question there. Moving on to Patrick in Parkhurst. Do you want to talk about life beyond Earth, Patrick?
Yeah, I was wondering what sort of seeds they're going to be taking to Mars for that colony they're setting up there or planning to set up. And would they be taking plant cuttings or actual seeds to grow? And what sort of hydroponic systems will they have in place that could maybe, and also what sort of technology they're going to be taking with them? Like we got the solar panels, we got quite a lot from space exploration. Thanks.
Now, the answer to this is a complex one, and the answer is we don't have all the answers because no one's ever done this. But there are people doing experiments to simulate how plants will grow in space and also on other planets. Now, plants have evolved to grow on Earth, and so anywhere other than Earth is a completely alien environment to them, and they're not going to be very happy because plants have a body clock, just like we do. In fact, some of the first observations were made on how animals and organisms keep time were made on plants, showing that they still knew what time of day it was, even if you grew them in a box without any light. So plants have a body clock. So if you take them into space, they're going to get jet lagged. If you put them on another planet that has a different day-night cycle to the Earth, they're going to get jet lagged, and that means they're not going to grow very well because in the same way we don't function, when we're jet lagged, they don't function very well either. But plants are essential because they are nature's solar panels. They have the ability through photosynthesis to collect the energy and light and to turn that into important chemicals that we can use in our bodies to keep us nourished and to grow. So we regard plants and the ability to grow plants as absolutely fundamental to our survival on distant worlds and up there in space. Now, people are simulating these environments. We know, or we have a reasonable insight into what the soil, in inverted commas, is like. I would say the Earth, but that would be the wrong word, wouldn't it? The Earth is like on Mars. So we can make our own Martian soil in the laboratory. Scientists are doing that. And you can therefore see what you would have to do to manipulate it in order to make it as Earth-like as possible. And therefore, you can do tests to see how Earth organisms will grow in that particular environment. People are doing that. In terms of actually powering our presence on Mars, there's a certain amount of energy arriving from the sun, and you could do some degree of solar capture, fair enough, but it probably isn't going to be enough to do very much. So we may have to take some kind of nuclear energy source or come up with a way of using nuclear energy to provide enough power to keep people warm, keep people fed, and also to provide water and fresh air for people, because as experiments have shown, it's very difficult to, in a closed environment, get enough plants growing to recycle enough carbon dioxide to have a stable environment like we do here on Earth. So we're going to have some kind of chemical assistance to produce enough oxygen for us to breathe and to get rid of the extra CO2, the carbon dioxide that we're all breathing out when It's dark and the plants aren't taking any in, and just because we'll be living in quite close-quartered confines anyway. So there's a whole range of challenges, but because we have a reasonable insight into what Mars is like, including what the soils are like and what the temperatures are like and so on, we can begin to model that here on Earth and then work out what we need to do to make the most of the raw materials on Mars so we don't have to take too much with us, but what we're going to have to do to adapt plants to make them grow in that environment. And there are scientists actively doing this now.
If you just joined us, Chris Smith, the Naked Scientist, is with me, Nicholas Bauer, standing in for Eusebius Mkhize. Joy on the WhatsApp line, Chris wants to know, why is water boiled on gas as opposed to electricity different? It seems to make coffee so much nicer. Is there any merit in that hypothesis?
Well, energy is energy. And in both cases, if you're burning gas, you're producing thermal energy, which you're conveying into the water. If you're using electricity, it's actually probably quite wasteful to use electricity if you could use gas, because you've already burned something to make the electricity, and therefore you've already lost some energy. But in both cases, you're imparting energy to the water, and that imparting of energy raises the temperature and you boil the water. Now, in terms of whether or not they're going to taste different, the difference here is that a gas flame is going to heat the base surface of the kettle, and it's going to convey the energy through the base of the kettle or saucepan. With a kettle that's an electric kettle, you have an electric heating element. The reason this is so noisy when you first put it on the heat is because the element starts to make the water get very, very hot around the element, but it's cold elsewhere. So you make these bubbles of water vapour around the element, which quickly rise away from the water element, very quickly get cold and collapse in on themselves, and they make those knocking and banging noises. That shouldn't, though, affect the flavour in any way, or the taste. What it might do, though, is that you might extract more hardness or temporary hardness from the water and make chalk in your kettle if you have a very focal point of heat like an element. So it's possible that you get more scaling around the element, and that pulls more minerals out of the water in the electric kettle, but I'm completely speculating with that one. I don't know for sure if that's the case. I suspect it's more a psychological thing, if I'm quite honest.
Fascinating stuff. Interesting hypothesis indeed. Well, Chris, I hope you can stay a little bit past 10:30. There's so many calls in here. Let's see if we can get through them. Kingley in Pretoria, you want to talk about sleep paralysis. Good morning.
Yeah, I have a question on that. Like, how does it really work? Because, you'll be sleeping and then all of a sudden you can't breathe, or you get a knee check, and it's really traumatizing.
Good morning.
Chris, you get that?
Yeah. This is all about sleep paralysis, and it's a real phenomenon. When we go to sleep, there's a part of the brain stem, it's in a region called the subcerulear region, which suppresses the flow of movement information from the higher parts of your brain down your spinal cord. The idea being that when you are sleeping, you don't want to be acting out your dreams or sleepwalking, because this could be dangerous. So certain groups of muscles, not the respiratory muscles, obviously, and not all muscles, are suppressed when we go to sleep so that you don't have execution of movements which would lead to a disturbed night's sleep. Now, what can happen is that when you wake up, the circuits that wake you up and make you aroused and conscious might not sometimes, in some people, kick in at the same time as you lift the brakes on this flow of motor information from the top part of the brain going down the spinal cord. So there can, in some people, periodically be this situation where you wake up and you're aware, but because you still have this gating of the information, stopping it going down your spinal cord, you can't move. And people find this very frightening, because you wake up and you think, I'm locked into position. I can't move. I can't do anything. I'm paralysed. And then that repression is lifted and you're fine. Now, most people have experienced this actually, because you may have had a dream where you've been trying to run away from somebody or something or do something, and you find that you've become ridiculously weak, and it's like running through treacle, or you try to thump somebody and your arm barely moves. And this is that effect. It's that the body is registering what should be happening and registering what actually is happening. It compares the two, and it realises there's a disconnect in your brain, and it says, well, look, I'm not getting this action coming back that I'm expecting. I must be very, very weak. So you actually are conscious of the fact that this is happening, including in your dreams. So it's a very real phenomenon. Fortunately, it's quite rare, and it doesn't harm you in any way. As soon as the situation switches off, you go back to normal. You're not going to be paralysed in any way permanently.
All right, that was from Kingley in Pretoria. David in Bella Bella, you want to talk about asteroids?
Yes, exometeorites, metallic meteorites. If they hit the ground at a very shallow angle, at high speed, a large meteorite, about 20 kilometers plus, how far could it travel underground, under the Earth's crust?
Oh, David,
Thanks very much for that one, David.
To be completely frank with you, I have no idea about the answer to that question. The bottom line is something with that much energy is going to create an enormous hole in the Earth's surface. And I don't think it's necessarily going to get very far because most of these things just smash to pieces as soon as they come in, because they're coming in at enormously high velocities. And as soon as they hit the ground surface, they're going to convert all of that kinetic energy largely into heat. So they're going to smash apart and they're probably going to melt. So I don't think they're going to go very far. But if there is an Earth scientist who can help me out and actually knows the answer to this, how far these impactors go underground, then do tell us. I mean, if you have something which is absolutely enormous, and winding the clock back about 4.57 billion years, there was an impact between the Earth and a planet almost the same size as the Earth. It's notionally called Theia. And one theory of where our moon came from, it seems a pretty good one, is that these two planets ended up on the same orbit as each other, and one ran into the other. And this cosmic collision achieved two things. One, most of the core of this other planet ended up sinking into the core of the Earth, and most of the crust of the Earth ended up being ejected into orbit around this new nascent body we're calling Earth, which is the product of the collision of these two bodies, and that coalesced to form the moon, which is why we have such a big moon relative to the size of the Earth. So if you have an enormous impactor, then that certainly can get a long way underground, but I would think something about 20 kilometres across is big. It's big enough to produce changes that we would be able to measure, but it's probably not going to make it that far into the crust. But if anyone knows different, please do tell me.
702. The Naked Scientist.
Let's go to Fani in Olifantsfontein, or beg your pardon, before Fani, Bongani and Randburg's been holding way longer.
Yes, I just want to ask Chris, when the supersonic jet travels and it passes I think it's a 600 knot speed, there's that glowing bang sound outside that you can clearly see on the game, but I thought I saw it on the aircraft investigation. Why is that? What makes that glowing bang sound?
Morning, Bongani. The reason for this, it's called a sonic boom, and it's because sound has a finite speed in air. So the way to think about this, if you imagine the aircraft producing sound waves, the sound waves leave the aircraft at the speed of sound, which is 767 miles an hour, and they come towards you. They can't go any faster than that. Now, if the aircraft is moving at close to that speed, as soon as the sound tries to leave the aircraft, it can't get away any faster than the aircraft is moving at. So the next sound wave that comes along catches up with the sound wave in front, and the two then add together, and the next one, and the next one. And so when you, as the observer, see the aeroplane go over, the sound waves coming from the aeroplane don't arrive in a sequence, they all arrive together. And you get this very big displacement, this big release of energy, so you have a very loud sound. And these are seriously devastating, these sonic booms. They can actually break windows, do damage to buildings, and they're also very frightening for people. So military jets and things that are capable of doing this are not allowed to fly like that unless it's an absolute dire emergency, or they do it where there aren't people around. And it isn't just aircraft that can do this. If you remember the Chelyabinsk meteor that came in over Russia about 5-6 years ago, this broke up in the atmosphere, but it was coming in so fast that the fragments were breaking the sound barrier. They unleashed a sequence of sonic booms over that part of Russia, and there was damage to buildings because the energy in those shock waves, these lots of sound waves all arriving at exactly the same moment in time, broke windows in buildings and did damage. Very spectacular, very awe-inspiring, but also not particularly pleasant for people and animals who have to listen to them.
Thanks very much for that question there, Bongani. Maybe a quick one off the WhatsApp line. We've got Jovan in Benoni asking here, Chris, if it's possible to change your subconscious, and if it is, how do you go about doing so?
To be honest, I don't know the answer to that question in the sense that what is our subconscious? Our subconscious is the way in which your brain actually works without you realising. Because our consciousness is a sort of veneer over the top of all the processing that's happening in our brains, and the brain selects information and presents it to our consciousness while screening out stuff that it thinks we don't need to know about. A good example of this is, I guarantee there are lots of people listening to this program who have had the effect where you've driven somewhere. You might have driven home or gone to work, and you've been thinking about something along the way. And when you got to where you were going, you suddenly realised that you'd done all these manoeuvres, negotiated roundabouts and traffic junctions, and you can't actually remember doing any of it. Equally, I guarantee the majority of people, I hope the majority of people listening to The Naked Scientists are actually wearing clothes at the moment, but most people are probably not thinking about the clothes that are on their bodies. You're not aware of your underpants, for example. But now I've mentioned it, you suddenly think, oh yeah, I can feel my underpants. And this is because your nervous system is screening out a lot of the information that you don't need to know about. It keeps on presenting to you things that are changing, things that you need to be aware of, but it's ignoring and suppressing a lot of other stuff that if you tried to attend to everything, you'd have sensory overload. So that's your subconscious doing that, and that's an automatic system over which you probably can exert some control with training, but how effective actually changing the way your brain processes this sort of information, I don't know the answer to that. And maybe there's a psychologist who can give us some clues, who's listening, but I don't think that actually there are some aspects. I think there are some aspects of this that are hardwired into us and we can't do anything about them.
Let's go to Dirk in Edenvale. Dirk, you want to talk about firing bullets?
Yes, I would like to know that if you fire a bullet into the air, how high will it reach? And when it starts turning down to earth, what will the velocity be? And is it possible to kill you when it lands on your head or something?
Morning, Dirk. This is something that actually has been tested. Because the physics, if you did this on a planet like Mars with a very thin atmosphere, you fire a projectile straight up into the air, when the bullet first leaves the gun, it has a lot of kinetic energy. It's moving. And it will go upwards in the atmosphere, doing work against gravity, which is trying to pull it down, until it's converted all of the kinetic energy, the movement in the bullet, into what we call gravitational potential energy. It's equivalent to you rolling a stone up the hill. So when the bullet comes to a stop, which it will do instantaneously at some height above the Earth, it'll be, kilometres up, then at that point it's being pulled down very hard by gravity, and it's got all the time it's going to take the bullet to fall back to Earth to be accelerated again by gravity. And in theory, assuming that there's no losses to air resistance, it would end up coming down and reach a velocity coming down the same as the velocity it left the gun at. So, if you were underneath that bullet, you could potentially shoot yourself in the head, and you would be killed, because the bullet would be going as fast as if you just held a gun to your head. So this is why people are told, don't do this, because the bullet could actually come down at very high speed and will certainly injure someone. Now, the reality is a little bit different, because on Earth we have a relatively thick atmosphere, and as the bullet goes through the air, it's doing work against the air, pushing air molecules out of the way. This is called friction, and that friction means that the bullet loses some of its kinetic energy, turning air molecules into hotter air molecules. So although the bullet does go very high, it's lost energy on the way up. It then loses energy again on the way down, so by the time it's coming back down, it's not going at the same speed as it would have left the gun at. It will be going considerably slower. That's not to say, though, it could still be going sufficiently fast to do harm to somebody. And people have done experiments on this, and it's unlikely you'd probably kill someone, but you could. And so it's a very bad idea to fire guns and other things straight up in the air, because what goes up must come down, and it will come down very hard and could come down lethally. So please don't do that.
All right, thanks for that one, Dirk in Edenvale. Let's go to Patedi, rather, in Kempton Park. Patedi, good morning.
Hi, how are you?
Always good. Go ahead.
Good, man. Look, Naked Scientists, I just want to find out regarding carbon emission theory, that the carbon that we burn from the coal actually damages the environment. So what I want to understand is, as much as the carbon that we got in the hole is the same carbon that was there in the atmosphere prior to the plants dying and going through the process of fossilification and all that. So I just want to understand, why is it that the carbon that the trees got from the atmosphere, when we burn it now becomes harmful to the atmosphere.
Yep, I understand where you're coming from. So your point is that plants photosynthesize and they pull carbon out of the atmosphere and they turn it into the wood in the tree and the plant and so on, and that then gets turned into coal. So if that carbon dioxide was in the atmosphere to start with, why is it so bad if it's back in the atmosphere now once we burn that coal and release the carbon back into the atmosphere? Well, the reason is that coal, which has been underground for millions of years, takes millions of years to accumulate. And so locked up in a big coal field, or an oil field for that matter, because that's another form of carbon, is carbon that's millions of years of accumulation. Yet we're burning it in hundreds of years. So we're putting back into the atmosphere carbon dioxide all at once that actually has been removed over millions of years and sequestered in one place. And this is the problem, that actually you're increasing the amount of carbon in the atmosphere more than it's actually due to be there. Because when those trees and plants were growing, there was a certain amount of carbon in the atmosphere that they then locked away and turned into coal, and that coal was removed from the equation. So what we're doing is increasing the net amount of carbon in the atmosphere. And this is a problem because carbon dioxide as a molecule is actually very good at trapping energy. It's relatively good at absorbing infrared energy, and it therefore keeps the Earth's surface at a higher temperature. Normally, the energy from the Earth's surface would beam off into space. It'd be reflected into space, and it'd be radiated into space, and the planet would be a bit cooler. If you have this blanket of CO2 in the atmosphere, then instead of the energy just being radiated out into space, it instead gets interrupted by the carbon dioxide in the atmosphere, which absorbs some of that energy, so less leaves the planet, destined for space, and this means the planet is a bit warmer. And that increased energy in the atmosphere drives things like storm systems, and perhaps what's happening in Mozambique and Zimbabwe has actually been a consequence of increased energy in the atmosphere. We've seen an escalation in hurricane frequency and hurricane intensity in the Gulf of Mexico, for example. We also think that this is because there's more energy in the atmosphere. So it is a worry, and this is why we have to be careful about how much carbon's in the atmosphere, because it is strongly linked to the temperature of the global system.
Fani, you want to talk about things going wireless?
Hi, I just want to find out, we have so many things wireless, like wireless internet, wireless, almost plenty things. How far are we from having wireless electricity?
Well, it does exist. People have demonstrated that you can transmit power wirelessly. And in fact, anyone who's got a toothbrush that you don't have to actually connect to a wire, you just put it on its base station. There are also mobile phone chargers that work the same way. This is a demonstration of this. The energy is transferred in these situations by using an electromagnetic field. So basically you have a coil which you pass an alternating current through that coil, and this producing is, because it's an alternating current, a changing magnetic field. And if you then put another coil in that magnetic field, the second coil feels the changing magnetic flux, and it picks up or sees a current induced in it, and that's how you harvest the energy. But actually, these systems are relatively inefficient, and they don't work over long distances. So it's not easy to transmit large amounts of power over very long distances, certainly with the kinds of devices that we have at the moment and the energy consumption that we have at the moment. But there are other ways to do this. For instance, we've made lighting much more efficient by using LEDs. And so now you don't need big bulky cables to transmit energy to an LED. You can use the same piece of cable to carry data around the house and to send a little bit of power to an LED light, for example. So there are going to be better ways of transmitting energy around, but probably we're going to be hooked on cables and possibly fibre optics for quite a while yet.
Thanks very much for that one, Fani and Olifantsfontein. We got one voice note there. Do we have it lined up there, Abel?
Good morning, Naked Scientist. It's Tammy from Alberton. I just want to ask, what makes these continents to split apart and we have seas and oceans in between? And I want to ask, are we likely to have like sort of Africa split into to be in two continents and we have an ocean or a sea in between it? Thank you.
All right. So you get that one, Chris?
I did. Now, in terms of why continents divide, reasons other than political ones, this actually goes back to the fact that the Earth is not one solid static surface. It has tectonic plates. And this theory was first proposed back in the 1800s. when people looked at various configurations of the Earth's surface and volcanoes and things like the Galapagos Islands, where there appeared to be volcanoes and then extinct volcanoes. And they realised that probably the extinct volcanoes were where the Earth's surface had moved away from a hotspot, and you had a new volcano now over the hotspot, and the old islands that have moved away were the vestiges of these volcanoes. So they realised that the Earth's surface is continuously moving and reconfiguring itself. And what modern geology now tells us is that the Earth's surface is broken up into a series of plates. We call them tectonic plates. They're very thick, dense crust material that goes down hundreds of kilometres, and these are floating on a squidgy thing called the mantle, and they move, and their movements and migrations all over the Earth's surfaces are driven by various forces, which are partly because of the fact that they're floating on this squidgy mantle material. And where these plates meet, because some of these tectonic plates are moving in one direction and others are moving in another, this actually leads to either the pulling apart of some boundaries between them, or the coming together of other boundaries. And when you have a pulling apart, you get a rift, and this is like the East African rift. And when you have the two faults coming together, or the two boundaries coming together and moving towards each other, you can actually get either a subduction, where one swallows the other underneath it, and you tend to get volcanoes along that line, or the two push up and you get mountains. The Himalayas are a really neat example of this. India, believe it or not, about 60 to 100 million years ago, was right down where Antarctica is. And India has made its way right the way up across the Indian Ocean, pushing seafloor up in front of it as it went, and then ramming itself into the plate of Asia and pushing up the Himalayas. So we have, Himalayas for the last 60 to 100 million years, which weren't there before. And this is an amazing phenomenon, because when this happens, it actually changes the climate quite dramatically, because you disclose various rock types and minerals, and this changes how much carbon dioxide there is in the atmosphere, because the carbon dioxide reacts with various minerals that are being pushed out of the seafloor, and drawing down CO2 or releasing CO2 because of these activities changes the climate. So this is why we have these interesting geological epochs as well, with ice ages and warm periods and so on, because of the continuous migration and movement of these tectonic plates.
Chris, always an enlightening experience chatting to you. We're unfortunately out of time there, and no doubt the next time we speak, Brexit will still be going on. All the best. Have a nice weekend, and try and stay out of the...
Don't go there. It probably will. It probably will. And I'll have left the country by then in desperation.